Hey there, astronomy students. This is Miss Ruark. This is podcast 7.1. We're going to start getting into stars and what they are, how they're made, and pretty much get through the evolution and the life of a star. So let's start off with what exactly starlight is and what it's made of. So starlight and temperature is closely related. Stars are going to be made of gases, of course, and the temperature of the gas is determined or is a measure of the average kinetic energy of the particles of that gas. Okay, so the temperature of that star is going to be the defining characteristic of that star. If you know the temperature and you know some other properties such as size, you can understand the star. However, if you know the size but you don't know the temperature, you really can't understand the star. Okay, so we're going to talk about the different colors that they have for stars and what that means. Okay, so here's just a little chart over here that shows you that, just to give you a heads up, the color blue would give us a very hot star. White's going to be hot. As we continue to go down towards the red, it's actually going to be a cool star. It's not very hot at all. All right, origin of starlight. So the origin of starlight or the light that comes off of a star, such as our sun, comes from the photosphere of the star, and that's the gases in the outer surface layer. Okay, remember the photosphere is this outer surface, okay, often called the surface of the star, and it's where the light is given off. Okay, photons actually come from they're made from changing electrical fields, and they're given off. Photons are just packets of light. It's little particles or little packets of energy. Okay, and so how can you make those photons happen? How can you change the electric field? Well, you can do that by disturbing the motion of the electrons in the gas particles, then that will produce electromagnetic waves. And you can also produce more photons by increasing the temperature. If you increase the temperature of a gas, you increase the kinetic energy. If you increase the kinetic energy of a gas, you increase the collisions that those gas particles would have with each other. And by colliding those particles together, you can disturb the electrons, make them very unhappy. All right. Black body radiation is going to be any type of radiation that's given off by a heated object. Okay, so everything would be considered a heated object or a heated body, because anything that has a temperature above 0 Kelvin is a heated body. Okay, well, everything has a temperature above 0 Kelvin, because 0 Kelvin is when all motion ceased to exist. All right, so all molecular motion would stop. It would just stop. And that's not possible. So everything is a heated body. If you increase the temperature of a body, let's just put it that way, or a substance, you're going to increase the black body radiation that's being given off. It's pretty easy, right? And the wavelength of radiation that's given off, that's being released, depends on the violent nature of the collisions of the particles that's happening. Okay? And so that helps us to determine the temperature of a substance. Okay, so here I have a black body radiation curve, okay, and it shows you that the intensity is increasing as you go up, and the wavelength is increasing as you go sideways. So the shortest wavelength would be UV, and the longer wavelengths would be infrared. Okay, it's showing us that here, this would be the sun, the surface of the sun, and it gives off that yellow light, but it also gives off other colors, but it gives off that yellow light because it's roughly at about 600,000 or 6,000 Kelvin. Okay, well, we also have a carbon lamp, which would be here, this little arc right here. This would give off, the highest peak would be at 4,000 Kelvin, which is in the infrared range. And then another type of lamp would be here in the 3,000. It's another infrared lamp. Okay, there are others where that peak comes up. That's how they determine the temperature of the surface of that star. Okay, so you can use this type of radiation or this type of curve, and we'll look at some. Hopefully, if I can get my hands on them, we'll look at some more where you can actually use it to determine the temperature of the substance that you're looking at. All right, well, there are a couple radiation laws that you need to know about. Actually, let's go back to this one more time. Let's come back here one more time. Okay, this will help you determine the color of the star also. I wanted to make sure that we turned that out. So, or pointed that out. So if you increase the temperature of the star, notice that it's decreasing in the wavelength, and here you would have your blue stars, which are your hottest stars. Okay, if you were to decrease the temperature of the star, because this here is about 6,000. Well, here it would be at about 20,000, and it would keep going. Okay, so this also shows you how if the increase in temperature, because let's say that a blue star would probably be about here or higher on this, okay, and then notice how there's a decrease in temperature, and it goes from blue down to red, and then the red would be, of course, the cooler stars. Okay, so Betelgeuse in Orion is actually a red star. It's very cool. And then Rigel is another big star in Orion, and it's actually going to be blue. It's hot. Okay. All right. The radiation laws. There's 2 radiation laws that they use in order to talk about the energy and the color of a star. Okay, the first one is the Stefan-Boltzmann law, which deals with energy, and it says here that the energy. Oh, here it is. The energy is equal to, this symbol here stands for the radiation that's emitted by 1 meter squared in joules per second. It's actually a constant. And then this would be the temperature raised to the 4th power. So this is telling us that a star that has the same size as the sun, as our sun, but it's 2 times as hot, is actually not going to give off 2 times more heat or radiation than our sun. It's actually going to give off 2 to the 4th times more, or 16 times more energy. Okay, so it's showing that it increases by an exponent of 4. It's not going to be the same. All right, and then Wien's law is dealing with color. Okay, and this is telling us that the maximum wavelength, or wavelength of maximum intensity, depends only upon the temperature of the star. Okay, so this would be the speed of light up here, and we use this to relate wavelength and temperature. Okay, so for example, a star with a surface temperature that's equal to 3,000 Kelvin would give off radiation in the near IR range at about 1,000 nanometers. Okay, so the hottest stars that there are in the solar system, not in the solar system, excuse me, in the whole universe, radiate typically in the UV range. Okay, so the UV range is going to be extremely hot, and this 3,000 star is not going to be very hot. Our 6,000 star, our sun, radiates in about the, if I believe I'm correct, I think it radiates in about the 400 range, but I'm not positive. We'll look at that again. I don't have my numbers in front of me. All right, atoms. So let's do a little chemistry lesson here. Atoms are made of subatomic particles. They have protons, neutrons, and electrons in them. Okay, protons are positively charged, neutrons are negatively charged. They're both inside the nucleus. Then you have your electrons floating around on the outside, and they are negative charged. So typically you have a neutral atom because it has the same number of protons as it does electrons. Okay, the protons and the neutrons have the most mass, so the mass of the atom comes from the nucleus. Okay, if you were to take the electron has so little mass when compared to the protons and the neutrons that it would be as if you went to the doctor and you said, he took your weight, and then you jumped off the scale and you rubbed your eye and you noticed, oh, I lost an eyelash. Let me get back on there and take my weight again. Well, you wouldn't do that, right? Because the eyelash doesn't weigh that much. Its weight is insignificant. Okay, and so the eyelash would be representative of that electron. Okay, that electron has so little weight in comparison to the protons and the neutrons, it doesn't really matter. So we say it's negligible. Right? Okay, so the mass of the atom will come from the nucleus. However, the electrons don't like to be near each other, and they spread out in these big, huge electron clouds, and so the volume of the atom comes from the electron cloud. Okay, to give you some perspective on that, if you were to go down to the stadium and we're sitting and looking at the football field, if we were to take one of those little English peas, that's a little green pea, and we're going to take that and stick it in the middle of the field on the middle of the 50-yard line. Okay, and then we spread all the way out, and we're sitting up at the top near the concession stand. Okay, if you're looking down at the field, you would not be able to see that green pea. but that green P would be your nucleus. The remainder of the field and the stadium and all the way up through the concessions would be your electron cloud. Okay, so the volume comes from the electron cloud. All right, well, we can adjust these subatomic particles. Well, we can't, but we can. Okay, so if we change the number of protons, we're actually changing the identity of that element. Okay, because all of these subatomic particles come together to form atoms, and the atoms form elements, such as hydrogen, helium, lithium, boron, germanium, tungsten, plutonium, uranium, they're all formed from atoms. So if we change the number of protons, which tells us the identity of that atom, we're going to change the identity of the atom. So if we have 6 protons, we have carbon. If we have 8 protons, we have oxygen. If we have 3 protons, we have lithium. All right. If we change the number of neutrons, we're actually going to end up with what we call an isotope. So an isotope happens when you change the number of neutrons. Neutrons are neutral. They have no charge, so they don't affect it in an electrical sense. They affect it by mass, because those neutrons are so massive that if you change the number of neutrons, you change the mass of the atom. And then ionization is when you change the number of electrons. So if we take an electron away, we're gonna form an ion. And we can actually add electrons as well, and we can form an ion. And when you take them away, typically they're formed by violent collisions. And in order to take 2 atoms and bond them, they have to collide. But these violent collisions are so violent, and they happen at such high temperatures in the stars that it's not favorable for bonding unless the star is a cool star. Okay, so how does this work with the atom and light and matter, and why are you telling us about this? Okay, well, the electron cloud is where the energy levels of the atom are located. Okay, the lowest energy levels are the ones closest to the nucleus, and as you get further from the nucleus, the energy levels get higher. Okay, so the first one at the right around the nucleus here, this one here with these 2 electrons, that first one, that would be energy level 1, and then energy level 2, and then 3, 4, 5, 6, 7, and keep going until you, yeah. All right, and these electrons can go from one energy level to another, but they have to have energy. Okay, so this electron here can actually jump from this energy level all the way out to one out here. It would just have to gain a certain amount of energy to make that jump. And then to jump back down, or to go down to a lower energy, well, let me back up. Once it jumps up in energy level, now it's an excited atom. It's excited. Okay? Why? Because it has all this energy. It's just excited, right? Okay, and then it's unstable, so it's got to get rid of this energy, so it's going to release it. When it releases that energy, it goes back down in energy level. It can release all of that energy, or it can release part of that energy. And the amount of energy that it releases is given off in the form of light. Okay, so that's where you end up seeing, well, the stuff that we can see is given off in the form of light. Sometimes it's given off in other forms, but most of the time it's Roy G. Biv. Okay, so we see those colors that are being given off by the electrons. Okay. When we see them, they're given off in what we would call a spectrum. There's 3 types of spectrums. There is a continuous spectrum, there's a emission spectrum, and an absorption spectrum. So the continuous gives all the colors, and it's given all the colors that are given off as black body radiation. The emission spectrum is where the photons are emitted by the gas, but when they come through, you're only seeing the photons that are being emitted by the gas. You're not seeing anything that's given off from the source. Okay, so it's when it's passing through a gas and it's actually making its way through. Okay, and then the absorption spectrum is showing all the stuff that's coming from the source, but it's also showing, or it's not showing, all these black lines here are, here it is. All these black lines here are showing where the photons have been absorbed. Okay, so there's 3 types of spectrums there. All right, let's get through this real quick, and then I'll do a second one. So stellar spectra will give you have Balmer thermometers, which can detect medium temperature stars. Hot stars and cool stars have weak Balmer lines because it can't detect between a certain wavelength, or it doesn't detect strongly after a certain wavelength. And Balmer thermometer lines are used to determine the temperature of stars. And I'll try to pull one of these out next class so that you guys can look at them, and we'll talk about them more in depth there. All right, so this is going to be the end of part A, because apparently there's too much information to put into one, and then you'll just need to watch part B in just a minute. And that's that.